Hi, everyone. Hope everyone is okay. Welcome to the Mr. X free online class for grade 12 physical sciences. In this particular class, we are dealing with past exam papers under the topic of momentum and impulse. Very exciting topic, but also I've got very exciting news because I will be starting the Mr. X online group classes where the magic happens, where distinctions are produced, where level 3s become level 7s, level 2s, go all the way up to the 80s and the 90s, where I can save you, as I usually say. These will be a continual thing the whole year, starting from the 2nd of February. I'm doing grade 11 and grade 12 classes for mathematics and physical sciences. 5 classes per month, each subject. We're looking at 250 rands per subject. Mondays is mathematics, grade 11. Wednesday, physical sciences, grade 11. On Tuesday, it's mathematics, grade 12. Then on Thursday, as you see on the right-hand side of the poster, it's physical sciences, grade 11. Every lesson starts from 7 p.m. to 9 p.m., recorded as well. So it's going to be an exciting time that we have. Book your spot. Limited spaces available. Mr. X can save you. Interestingly, this is what the February schedule looks like. The topics that we're going to be doing according to the annual teaching plan, making sure that all of you get to do, know, and understand. I can save you from failing. I can save you from messing up. I can improve your marks. So join the Mr. X affordable quality, and you'll never find that kind here in our country. So let's begin our lesson. Remember that. I'll talk about it also later on. Boom. Let's do this. What are we doing? Momentum and impulse. And what are we talking about? Past exam papers. So it's going to be question after question after question after question. We start with our first one. Let's go. It's the 2020 Senior Certificate Paper 1, and it's question number 4. Let's start on that one. Now, what is important when you're doing questions in physics is to be able to read the information properly, to note the key words, key numbers. So when you're reading a question, do note ball P, okay, of mass, now you know, 0.16 kilograms. So I want to write that one there. So ball P is a mass of 0.16 kilogram, is moving east. Momentum is very essential on issues of direction. So it's moving east at a speed of 10 meters per second. Then it collides head on with another ball Q of mass 0.2 kilograms, but the ball Q is moving west at a speed of 15 meters per second. After the collision, important words, after the collision, ball P moves west at a speed of 5 meters per second, as shown in the diagram below. We're given a disclaimer: ignore the effects of friction and the rotational effects of the balls. So there's my diagram. I see ball P moving to the east, and then ball Q moving to the west. There's collision. There's the before and the after. Also, they gave you cardinal points. So when they give you cardinal points, north, west, east, south, when you're speaking about direction, don't say to the right, don't say to the left, but rather use west and east as they've given you in the question. In every single topic in physics, even in chemistry, there's always a definition. Definitions are 2 marks or nothing. You'll get 2 full marks or you get a beautiful 0. 4.1, we need to know how to define. I'm reading. Define the term momentum in words. There is the answer. I took this from the exam guideline. So when looking for definitions, please, fam, always refer to the exam guideline, and that's how they want you to reproduce it. Momentum is the product of an object's mass and its velocity. Momentum is the product of an object's mass and its velocity. Write that one down. The next one is a calculation. Now we need to, when dealing with calculations, so this is the definition. When dealing with calculations, here's what's important. Please note that you need to gather your information. What do I have? That's the first thing that you must ask yourself. What do I have? Okay. What do they want? That's the second one. What can I use? One more time. What do I have? Okay. What do they want? All right. What can I use? Read the question properly. 4.2. It reads as follows. Calculate the velocity of ball Q after the collision. That's what they want. The velocity of ball Q after the collision. Now, when dealing with momentum, direction is very important. So it's important before you do anything to state your direction. Are you saying east is positive? Are you saying west is positive? And that's very important. Are you saying east is positive? Are you saying west is positive? That's very important. So I will say, let me take east as positive. That's the first thing. Now, as to what can I use? In momentum, the principle of conservation of momentum is your friend. It's the one that gets you places. That principle says that in an isolated system, the total momentum is conserved. In other words, the momentum initially and the momentum finally, the sum of, they are conserved. It remains constant. In the exam, once you write the statement, you get your first mark. I know other people would want to further on make it clear. Let me do so. So momentum, the mass of ball P, the velocity of ball P initially, plus the mass of ball Q and the velocity of ball Q initially. Then we go to final. Notice that after the collision, ball P moves to the west, and then other one moves as it is. So they are not moving together. That's a very important thing. If they were moving together after collision, then their masses, you would add them. But even after collision, they move out individually. So I'm ready. Mass of ball P and then velocity of ball P final plus mass of ball Q and velocity of ball Q final. You do not get an extra mark for writing this. You don't. Okay? You get a mark for writing this. This may help you to clarify the situation, but you do not get an extra mark for that. So let's put our story. What are we looking for? Velocity of ball Q after the collision. Now notice we said east is positive. So everything moving eastwards is positive, and by extension, everything moving west becomes negative. Mass of ball P, 0.16. Velocity of ball P initially, it's the 10 meters per second, and it's a positive 10. It was moving to the east. Plus mass of ball Q, 0.2. Velocity of ball Q is 15, but it has to be negative 15 because ball Q is moving to the west and west is negative. We said east is positive. Let's do some maths. After collision, mass of ball QP still 0.16, and we notice that ball P moves at 5 meters per second west after collision, ball P. So now the velocity is negative 5. Mass of ball Q, 0.16. Then the velocity, 0.2 rather, 0.2 for ball Q And the velocity of ball Q after collision is what we don't know. The rest is algebra. Get an answer on the left-hand side, right-hand side, divide, do the maths properly. I need a confirmation of the answer. Velocity of ball Q is negative 3 meters per second. Now hold on, negative 3 meters per second. That means it is actually 3 meters per second and it's moving to the west. This becomes your answer, 3 meters per second, and it's moving to the west. So write that one down, talk to me where there's a problem. Please confirm the answer from there on that. Okay, I'm good to go. Somebody has a hand, go ahead, I'm listening. Okay, rather type your question, which is what I prefer. Type, which is what I prefer. All right, perfect. Here we go. And we take it up from there. So it gives you a -3. And remember, the negative just shows you the direction. The actual value or the magnitude is 3 meters per second, but its direction is to the west. So that's your answer for 4.21. Let's try 4.22. Which is quite important because the more we do, the more we know. I'm ready for 4.22. Ask where you don't understand, confirm the answer. 3 meters per second, do your maths, put your answers there, and we take it up from there. Remember again, the principle of conservation of momentum is your game plan. It's your go-to guide when doing this particular questions there. So we always indicate the direction as is right there. Taking this out, let's try 4.22. 4.22 says, calculate the magnitude of the impulse on ball P during the collision. The magnitude of the impulse on ball P during the collision. I want to allude to this. As to the choice of the equation that you use, it will depend on the information that has been given. So your choice of the equation will depend on the information that has been given. Impulse, by definition, impulse, and we'll do it along the way, a question on impulse. Impulse, by definition, is the product of the force acting on an object and the time taken by that force to act on the object. I'll reiterate it. I've got a question that asks that particular definition. So in other words, I'm saying impulse, okay, is equal to force acting multiplied by time taken. Now, also in the same breath, impulse is actually the change in the momentum. That's what impulse is. So again, your choice of the equation will always depend on the information given. We are looking for the impulse on ball P during the collision. We don't know the force acting, so this formula cannot be used. We also don't know the time taken or the time of contact, so we can't use it. And I will keep reiterating, your choice of the equation depends on the information that has been given. Impulse is change in momentum. We're looking for the impulse on ball P. Ball P. Change in momentum, change is mass of an object multiplied by the change in velocity. The mass, then I'm looking at VF minus VI. Let's do some maths here. All right, work with me. So remember, we still take east as positive. That means west is negative. So the mass of ball P, we're looking at 0.16. Its final velocity is 5 meters per second west. So it's -5 minus its initial velocity, which was 10 meters per second east. So that's 10. The rest is algebra. I'm looking at the answer of negative 2.4 newtons seconds, which is a measurement of impulse. But I also want you to know this. Impulse can also be measured in kg meters per second. They love asking this in paper 1, the multiple choice. The units of newtons seconds and the units of kg meters per second are equivalent. Keep that in mind. They are equivalent. Newton seconds and kg meters per second, they're equivalent. So your answer is 2.4 newtons. I rest it there. Now listen to this. If you note question 4.21, we were looking for the velocity. In velocity, we wanted the actual magnitude, which is the value, and we also quoted the direction. Here, 4.22, they are saying to us the impulse, magnitude of the impulse. So you're looking for the value only. So there's a difference between saying calculate magnitude of the impulse and to say calculate the impulse. When they say calculate the magnitude, you just simply put the value. But if they say calculate the impulse, you put the value and its direction. So just to reiterate, if they had said calculate the impulse in question 4.22, would have said 2.4 newtons and would have said west. But they said magnitude, so this suffices. Somebody's saying, but say, what if I write both of them? No problem. You've over-answered, which is good. You would rather over-answer than under-answer. That's our first question. Talk to me. I think we're trying our best to make sure that we pull through. The more we do, and I tell you guys, the more we do, the more we know. The less we do, the less we know. We do more questions, we will understand more. I'm ready. Write this down. Let's move. This was our first hi, how are you type of question. Go ahead. I'm listening.
Hi, sir. Can you hear me?
Yeah.
Sir, don't we use the values for Q since they said on P and not off P?
All right. So you're asking, don't we use the values of Q in order to find the impulse that is exerted on ball P? You can use those of Q, you still get the same answer. I want you to understand that when there's a collision between two objects, when there's a collision between ball P as well as ball Q. Okay, let me just make it clear. This is ball P and ball Q. When there's a collision, the impulse exerted on ball P and the impulse exerted on ball Q is the same. This is in respect to Newton's third law. So the impulse, and even not just that, the force exerted, because force is the one that actually eventually causes the impulse on the object. So the force exerted on P and the force exerted on Q, when they collide, is the same. Equal in magnitude, but opposite in direction. And so does the impulse. So whether you use the information of P or the information of Q, you will get the same answer, because the impulse that P feels or is exerted on and the impulse that Q feels or is exerted on is one and the same thing in essence. That's our question. Thank you for that one. Let's move on to our next one. 2015 Metro South Prelim, and it's paper 1, question 4. Let's try this one. Always note the important things. So I'll build up the story, then I'll get to the difficult ones more and more as we go on along. I'm ready. It reads as follows. A wooden block of mass 2 kilograms moving at a velocity of 5 meters per second collides with the crate, so mass 2 kilograms moving at a velocity of 5 meters per second collides with a crate of mass 9 kilograms resting, keyword, on a flat horizontal surface as shown in the diagram below. After the collision, the crate moves to the right. The crate moves to the right at 1 meter per second, and they said ignore the effects of friction. Listen to this. You will notice that all the questions, almost all the questions, would have a disclaimer at the end. Ignore the effects of friction, ignore rotational effects. What it simply means is that you are working from the premise that the system is isolated. And if a system is isolated, then it means that the principle of conservation of momentum is applicable. When you define the principle of conservation of momentum, in some definitions, you put the idea that in an isolated system, in a closed system, and how do I know a system is isolated? How do I know a system is closed? Disclaimer, ignore the effects of friction. Dare I say, for your level, even if they don't put the disclaimer, always work from the premise that the system is isolated and the principle of conservation of momentum is applicable. That's my story. There's my diagram. I've got the crate, or rather the wooden block, moving at 5 meters per second to the right. This is the crate resting. Resting assumes the idea that its initial velocity is actually 0. Resting. So the initial velocity of the crate is 0. There is a collision, yebo, and then we notice that after the collision, the crate moves to the right at 1 meters per second, while we have the mass of 9 kgs. Now listen to something interesting. You'll notice that throughout the questions, what changes are the velocities, not the masses. The masses of the objects remain the same. What keeps changing over and over again is the velocities. The velocity before and the velocity after collision. 4.1 is a definition, 2 marks or nothing. Write down the principle of conservation of linear momentum in words. Right at the top there, taking all this from the exam guideline, and it states that the total linear momentum in an isolated, there's what I was talking about, in an isolated system remains constant, or you can say is conserved. All this from exam guidelines, our best friend when it comes to definition. Write this down. Much as you know the lyrics of certain musicians that you follow, right there. Much as you know our zep dance, lento foot. It's useless. Know this. Total linear momentum of an isolated system remains constant. Sing those words. All right, 4.2. Calculate the magnitude of the velocity of the block immediately after collision. Immediately after collision. Your best friend is your literal formula. Momentum initial, sum of, is momentum final. My suggestion, if you're not given cardinal points, about right and left, take right as positive. It's always an easier thing to work. Take right as positive. Let's do the maths. So initial momentum, that's the momentum of the wooden block, mass 2 kg, 5 meters per second is positive, plus the initial momentum of the crate, 9 mass, 0 is resting. Show that. You must show that it is resting. Momentum final, I've got the mass of the wooden block, but I don't know its final velocity. plus, then you've got the mass of the crate multiplied by a positive 1, that 1 being the fact that it's moving to the right at 1 meters per second. So this is what the scenario is. The rest is just algebra. We do the maths. And I'm thinking at the end of the day, your final velocity is 0.5 meters per second. Now notice they said magnitude. So writing this answer is okay. If you want to over answer and show them that you are going to varsity next year, just say to the right. But otherwise, suffice it to say 0.5 meters per second is okay as an answer. Magnitude. Magnitude. All right. Perfect. I'm ready for 4.3. I'm ready for 4.3. So the velocity of the crate is 1 meters per second after collision, but the one for the wooden block is 0.5 meters per second after the collision. 4.3. I want to reiterate something before I get to 4.3. I think one of you asked me prior, when looking for the impulse, are we not supposed to use the other ball? I think we had ball P and then ball Q. And I did say that the impulse is the same. Not just the impulse is the same, but the force exerted is the same, which is an extension or a certification of Newton's third law. So whether you use the information about ball P or ball Q, is going to be the same. 4.3, slowly we read it, we understand, we break it down. If the collision lasts 0.6 seconds, we've got the concept of time, 0.6 seconds. Calculate the force that the wooden block exerts on the crate during the collision, 4 marks. Calculate the force that the wooden block exerts on the crate during the collision. Now listen to me. The wooden block exerts a force on the crate, but also the crate exerts a force on the wooden block. And the force that the wooden block acts, or rather exerts on the crate, is the same as the force that the crate exerts on the wooden block. All right? So that's very important to understand. So whatever force the wooden block exerts on the crate is the same force that the crate exerts on the wooden block. So now we've got a problem. So whose information do we use? Do we use the information about the wooden block, say, or the information about the crate? My answer is either or. Let me show you how to, Bob, and you that the answer is the same. Let's start. Your choice of the equation depends on the information that has been given. Now, we notice that the force exerted multiplied by the time taken is equal to the change in the momentum. That's very important. So force times time is change in momentum. Your choice of the equation will always depend on the information that has been given. Fine. So I'm looking for force, yebo, and I have time 0.6. Change in momentum is mass of an object multiplied by the final velocity minus the initial. Let me use the information about the wooden block. The mass of the wooden block is 2 kilograms. Its final velocity is 0.5 meters, is positive, minus from the formula, its initial velocity is 5 meters per second, and all I'm looking for is force. So then just to make your life a bit easier, you'd have it this way. All of this over 0.6. Eventually, your answer is negative 15 newtons. So they want the force. So it will be 15 newtons to the left. I used the information about the wooden block. But I wanted to show you as well that even when you use the information about the crate, you get the same answer. Let's go crate. Force, the time is 0.6 seconds. All right, let me just put a multiplication sign there. Mass of the crate is 9. Its final velocity is 1. Its initial is 0. And all you're looking for is force. You get it as 15 newtons, and it's to the right. The numbers are the same. The values are the same. What is different is their direction, which again, I say, is Newton's third law of motion right there. So this is how you get it. Somebody's asking, say, if I leave my answer in fraction form, am I still correct? Yeah, but don't. Put your answer in decimals because they'll ask you to 2 decimal places. Go ahead, I'm listening. Guys, I'm unmuting you and you're not saying anything.
Okay.
I think type your question. Your network is tekering. Please type. I will definitely attend to it. All right. So what is important to do is, guys, when you're doing these questions, try to avoid having fractions. Put it as 0.5, 0.3, whatever the case could be. And then also as well, remember your choice of the equation will always depend on the information that has been given. So whether you choose equation of whatever, it is all informed by the details in the question. So I picked this one. Force times time is change in momentum. Change in momentum is mass of an object times velocity final minus initial. Eventually, you've got this part there. And I say to you, whether you're using information about the wooden block or information about the crate, it's one and the same thing. Either or doesn't matter. Conventionally, you can choose, and someone asking, said, do we always choose right as positive? Conventionally, it's always the case. You're not forced, but try to choose right as positive in cases where it is possible. Try to choose that. I'm ready for that one. Let's go. All right. Say, I wanted to ask if we don't choose directions for the velocities. That's a question. By choosing a direction in the beginning, you have chosen direction for the velocities. Anita, you said right is positive. That's what you say. Right is positive. That means every velocity that is directed to the left is negative. That's why you saw in, I think it was 4.2, I would put positive for right. And if there was a negative, I would have done it for the left one. In this case, everyone moves to the right. So that's why we have that situation. So you are safe to choose direction using the arrow, or you can just conventionally just take direction as positive. I would rather say let right be positive. In a case where it's not so clear, just say let the original direction be positive. So that's what someone is saying. Say, if they didn't give you the direction, are we not supposed to say let the original direction be positive? Yes, you can. In this case, they told you it's moving to the right. So that's why I chose it. 2023, Free State. The more we do, the more we know. The less we do, the less we know. I will give you stuff to try to hang on. Let's move. All right. I'm ready. Nothing hectic on this one here. So that is easier to understand. All right. Let's go. Let's do this. The question starts off. A 400-gram ball. Be careful, 400 grams. Mass is measured in kilograms. You would need to convert that 400 grams into kilograms. You divide by 1,000. A 400-gram ball is approaching a baseball player horizontally in a westerly direction. Cardinal points again. At a speed of 40 meters per second, as indicated in the diagram. The baseball player exerts a force of 400 newtons on the ball in an easterly direction. The ball is in contact with the bat for 0.1 seconds. Time taken, time of contact. Perfect. Our first question, I see the diagram, typical things that we see in the sports scene. Define impulse. Define impulse. There we go, right at the top. Impulse is defined as the product of the net or resultant force acting on an object and the time the net force acts on that object. Please write this down. These are supposed to be your daily verses, something that you speak, talk, memorize, recite, reiterate at any particular moment. The product, the net force act on an object, and the time taken by that force to act on the object. 4.11, we're good. 4.12, calculate the velocity of the ball immediately after contact with the bat. Calculate the velocity of the ball immediately after contact with the bat. Now, I want to make sure that this is clear. You need to choose a direction as positive. I will always prefer to the right as positive. To the right in this case is indicated by east. So I'll just say east as positive. That's what I would say. All right, sharp. What are we looking for? The velocity of the ball immediately after the collision. I know the velocity of the ball before collision. I'd like to know after. What do I have? What can I use? I have the force exerted on the ball. That force is easterly direction. I have the velocity of the ball before collision. I would need the velocity of the ball after collision. I have the mass of the ball and I have the time of contact. Your choice of the equation depends on the information given. I got your back. Net force or force, you can put it, multiplied by delta T is equal to delta P, which is the mass and the final velocity minus the initial velocity. Remember, the force is 400 newtons and is moving east, and we said east is positive. So I put my numbers now. So let me just put F net here, delta T. Let's put the numbers together. Let's go. 400 is a positive 400. The time, 0.1 seconds. Time is always positive. The mass is going to be 0.4. Remember, it's 400 grams, which you must convert to kilograms by dividing by 1,000. Final velocity, that is what we do not know. We know the initial velocity, which is basically going to be negative 40. I will say, speak to us. What's happening, brother? Talk to us here. Listen to me. The 40 meters per second is west. Our east is positive. So from the formula, you got a minus, but the initial velocity is a negative 40, meaning that it's moving in the opposite direction to what you said is positive. The rest is algebra, brackets opening, and so forth and so on. I would need a confirmation of the answer. You talk to me. You tell me, am I getting a positive 60 meters per second? Which means by extension, it's 60 meters per second is algebra to the east. They wanted the velocity. So I mentioned direction and magnitude. If they said magnitude of the velocity, I would have stopped here. Talk to me by confirmation. Yes or no? Is that 60 meters per second? All right, perfect. So that's good. Thank you. That's your answer. Let's go to the next one. The question continues. There's more dynamics that come together on this part. The more you do, the more you know. I'm ready. There's a big story coming up, and we take it up from there. Go ahead. I'm listening. I've unmuted you.
Oh, sorry, sir. I get 0.
No, it can't be 0.
So I want to understand, how did they get 60 meters per second?
You can't get 0. Okay, let me help. It's the maths. You do the maths, you do the calculation, you do the maths. Be very careful of that. All right, let me show you quickly, and we take it up from there. Okay, perfect. So this is 0,4. This is VF plus 0 plus 40, because minus and minus gives you a plus. And then this is 400. So you take your calculator, got 400 times 0,1, which you'll get as 40 right here. You've got many options, okay? So you can divide by 0,4 if you want. So I can divide both sides by 0,4. I get 100 is equal to VF plus 40 transpose VF is 60 meters per second. That's one way of doing it. There's another way. You can open up the brackets if you want. I didn't. I straight went up to getting that. So that's what we have, right? All right, perfect. Say, can you please explain why F net is 400? They gave me exerts a force of 400 Newton. Exerts a force of 400 Newton. All right, perfect. I'm ready. Don't forget that you're supposed to change the mass into kilograms by dividing by 1,000, and that's what we did. That's why our mass here is 0,4 kilograms. Ready? Another story. So just to note this, listen up that, please, the important stuff is to read the question properly, understand it, break it down until you get what is needed. Let's go to 4.2. It's a whole big story, and you take it up from there. All right, I'm ready. Let's do this. When cars are equipped with flexible bumpers, they will bounce off each other during low-speed collisions, thus carrying, or rather thus causing, less damage. In one such accident, a car with a mass, or car A with a mass of 1,750 kilograms, traveling to the right at 1 meters per second, collides with car B of mass 1,450, traveling to the left at 1.1 meters per second. Measurements show that the speed of car A after the collision is 0.25 meters in the original direction. Ignore the effects of friction during the collision. Again, once you see that disclaimer, it simply means we are assuming that is an isolated system. Same idea, and I'm building up with small things here. Then we'll go to our crazy stuff as we're going along. 4.21, calculate the velocity of car B immediately after the collision. Car B immediately after the collision. Our first one is to get our first mark. The total momentum before and after collision is the same. I'll take right as positive, which is what is preferred. Then from there on, we can break down to getting the numbers done. Mass of car A is 1,750. Its initial velocity is 1.5 meters, a positive one. Mass of car B is 1,450. Its initial velocity is a negative 1.1, negative because it moves to the left. There's collision. The car A moves in the original direction, still moves to the right. Car A its mass has not changed, 1,750 times 0.25 plus the mass of car B, 1450 times its final velocity. Then by extension, you will need to do your answers properly, get your numbers done. I think you should get the velocity of car B as 0.41 meters per second. It's a positive number, so it means it moves to the right. Can I please get a confirmation of that on that one day? Can I get a confirmation of that? 0.41, is that a yes or a no? So calculator, correct, confirmed, yebo, danko, spong. 4.21, that's your answer. Just try 4.22. 4.22. I'm ready for 4.22. 4.22 says the following. All right. Say, is it compulsory for us to indicate that right is positive before calculation? Yes. 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 When cars are equipped with flexible bumpers. Now, before I do this and read the question of 4.22, the concept of collisions and how to minimize the effect of a force when a collision takes place is a physics that utilizes the concept of time. Yo, say that again. I got your back. Whenever there's a collision, and to minimize the effect of a force on that in that collision, it's a physics of time. Let me show you. It's what you see in airbags, what you see in crumple zones, what you see in seat belts, what you see in arrestor beds. The whole concept is the same. Whenever there is a force, the force changes the velocity of the object, which means by extension, there is a change in the momentum of the object. In order to minimize the impact of the force, the time taken must be increased. When there's an increase in the time taken, there's a decrease in the force exerted. This all comes from the impulse formula, the one that says F net multiplied by delta T is equal to delta P. And so you will see, and I spoke about this in part one when I taught this in that video on YouTube. I say to you, if there is an increase in the force, the time taken to change the momentum of the object has to decrease. So if the time taken is limited or it's small, then it means the force required to change the velocity, consequently, the momentum of the object, that force becomes higher on account of less time. But if there is an increase in the time, then there will be a decrease in the force. And this is the physics of all safety features, from your seatbelt, arrestor beds, crumple zones, whatever the case could be. What you need to do is to increase the time of contact, you will decrease the force of impact. All this for the same change in momentum. And that's essential that you understand this. Time of contact is from that perspective. All right, I'm ready to pull this through. So listen to me carefully. Let's read the question. And this answer is applicable on any safety feature. 4.22. When cars are equipped with flexible bumpers. They will bounce off each other during low-speed collisions, and thus causing less damage. Explain, 3 marks, how flexible bumpers reduce damages during low-speed collisions. How flexible bumpers reduce damages during low-speed collisions. Let's visualize. When car A and car B bounce off each other and there is a flexible bumper, when they say a flexible bumper, is that type of bumper that when there's a collision, it kind of like absorbs, and this is lack of a better word, but kind of like absorbs the force that is exerted. It's flexible. The bumper that bends inward so that the time of contact between the two cars is increased. And when time is increased, the force is decreased for the same change in momentum. So the question for 3 marks says, explain how flexible bumpers reduce damage during low speed collisions. I got your back. Work with me. Check this out. Flexible bumpers, and I put this nicely, and I put the marks as well. Flexible bumpers, what do? They reduce the net force. Okay, how? By increasing the time required to bring about the same change in momentum. Here are your 3 guys. What's happening? What's happening? There's a reduction in the net force. Why? Because there's an increase in time. Increase the time. Decrease the net force for the same change in momentum. So the moment you decrease the time, then it means by the moment you increase the time, which means by extension, you're going to increase or rather reduce the net force. So an increase in time will reduce the net force, right? So that's a very important thing to understand. And you'll do this pretty much for everything. Whether you're dealing with seat belts or whatever the case, you'll do this for everything. Go ahead. Okay, I'm not hearing you. Yeah.
I'm still not understanding what flexible bumpers are, which leads to me not understanding the answer as a whole.
Okay. The concept of flexible bumpers is the idea that these are safety features that you find in cars, modern cars, which in the idea is that they absorb or rather increase the time of contact. I explained this also in my first lesson properly. They increase the time of contact. The moment the time taken is increased, the moment the time taken during a collision is increased, then the force exerted is decreased. The concept of increasing time will decrease the force. So again, the flexibility, or rather the equation, comes from this. F net multiplied by delta T is delta P. Increase the time of contact, decrease the force of impact. You'll find this also in sports such as boxing, even cricket, tennis, and all that. You find this when you drop from a high point to a low point from a tree. You don't land with your feet straight. You break them. You bend. Bending means the force, you are increasing the time taken between you and the ground. So the force that the ground exerts on you becomes less because you increase how long you spend with the ground. Increase time, decrease force. I preach that gospel. Increase time, decrease force. That's always the story. All right, I'm ready for that. And this is your answer. And you'll see this also in all aspects, and we take it up from there. All right, I'm ready for this one. 2018 senior certificate. So I'll run through a number of questions so that at least you can see how that goes. 2018 senior certificate, paper 1, question number 4. I implore you, please go and watch my first video where I was teaching this from basics. Okay? That way you have an idea. I think in the group, I say to you, if you don't watch that video, you're going to see spiritual things in this class. So please go and watch that one where I explained everything from scratch. Don't build from the roof, start from the foundation. 2018 Senior Certificate, Paper 1, question number 4. Write down the title and we go for it. It's an interesting question as well. So we need to make sure that we do this. Now, there's a topic that you're going to do in grade 12 called Work, Energy, and Power. Very interesting one. I have a video on it also on my YouTube channel where you can watch it from scratch, the basics. 2018 Senior Certificate, Paper 1, question number 4. I read. A trolley of mass 1.5 kgs is held stationary at point A at the top of a frictionless track. So point A there, the track is frictionless. When the 1.5 kg trolley is released, it moves down the track. Okay. It passes through point P at the bottom of the incline and collides with the stationary 2 kg trolley at point B. Refer to the diagram below, and it says ignore the air resistance and rotational effects. I'm on question 4.1. Let's read. Use the principle of conservation of mechanical energy. Mechanical energy. All right? Use the principle of conservation of mechanical energy to calculate the speed of the 1.5 kg trolley at point P. That's 4 marks. Now, don't confuse this. They say it's principle of conservation of mechanical energy, not conservation of momentum. Mechanical energy. Now, just to reiterate, this comes all the way from grade 10. Mechanical energy, EMAC. Mechanical energy is the sum of the potential energy and the kinetic energy. So when you speak about mechanical energy, you're talking about potential energy plus kinetic energy, whose formulas are what I'm writing here. All right, perfect. Mechanical energy can be conserved, but more specifically, mechanical energy is conserved on a frictionless surface. So when the surface is frictionless, in other words, there are no extra forces that act on the object, or rather, the system is isolated. When you have that situation, then the mechanical energy is conserved. And our question says, use that principle to calculate the speed of the 1.5 kg trolley at point P, which is this part here. So notice that the trolley is at point A, its mass being 1.5 kg. Then it is released. It moves down the track, gets all the way to point P, passes it, and then collides with another trolley, or collides with another trolley of 2 kgs. But for now, we're looking for the velocity right here when it reaches point P. That's whose velocity we're looking at. Fine. I'm okay from all of that. Now, having said that, we're looking for the speed of the trolley at point P. So now we say to ourselves, EMAC. EMAC is conserved. That means EMAC at point A. In some books, they say EMAC at the top is the same as EMAC at point P. And why am I using this formula? Why is it important that I use this formula? It is because I understand that there's a frictionless surface, that incline there, that track, and that means the mechanical energy will be conserved. So just to write, to make it sense, so it's going to be mgh plus half mv squared, all this at point A is equal to mgh plus half mv squared, all this at point B. That's the story. Mechanical energy is conserved. Now, at point A, we've got the mass as 1.5, G is 9.8, and the height above the ground, we're looking from the diagram, is 2 meters. So height above the ground at point A is 2. The initial velocity at point A is 0. Why, say? Because it was released. Released means that it's 0. You'll hear this word under the topic vertical projectile motion. An object is released, meaning that the initial velocity is 0, and therefore its kinetic energy will also be 0. So V is you must show that, is equal to, let's go to the information about point B. At point P rather, not B, point P, yes. At point P, the height above the ground is 0. That's why I'll write 0 for point P, because the object is on the ground already, so its height is 0. Half 1.5 multiplied by V squared. Be very careful of your algebra, because there's V squared. Don't forget to square it. I'm looking at 6,26 meters per second. So they wanted the speed of the trolley at point P, 6.26 meters per second, and that becomes your answer. Confirm, please. Say, please rephrase on why they are equal. Once the surface is frictionless, it means the mechanical energy is conserved. That's what it means. Therefore, the mechanical energy at point A and the point P is the same. You'll see this also again under the topic of work energy and power. The moment there is frictionlessness of a track, that means that the system is isolated, the system is closed. There are no exterior forces acting on it. Therefore, the principle of mechanical energy would be conserved. So mechanical energy is only conserved under the circumstance that the system is isolated. How do I know that the system is isolated? Well, it's a frictionless surface. That's how you know that the system is isolated. All right. Perfect. And all that. So remember, that's your answer. Remember, this is 1.5. 1.5 meters right there. 1.5. Do we indicate direction? They wanted the speed. Speed is a scalar quantity. That means that you're only talking about your magnitude. Speed is different from velocity. Speed is a scalar quantity. You're only talking about magnitude. Right, so this concept goes as far as grade 10, I think also grade 11, but it's also examined as far as grade 12. So that's what you have. So I'm good to that and all. All right, perfect. I'm ready. Let's go to the next one quickly, and we take it up from there. I'm ready. I'm ready. Go ahead, I'm listening. Guys, rather type your questions. I think your network is messing up. Rather type. Let me just put that as a disclaimer. Just type the questions. I will attend to them, because I don't like to be running through and then having to wait and all. So type the question. I'm ready for the next one. I'm ready for the next one. When the two trolleys collide, ooh, this is beautiful. When the two trolleys collide, I'm reading from this part. When the two trolleys collide, they stick together. They stick together. This is the first time we're doing a question where they stick together. They stick together and continue moving with the constant velocity. So they move together with the constant velocity. Then it says 4.2. The principle of conservation of linear momentum is given by the incomplete statement. In a dash system, the dash linear momentum is conserved. I think you know what I'm going to talk about. In an isolated system, that's the key word. I think they want us to rewrite rewrite the complete statement and fill in the missing words. Let me rewrite it. Let me rewrite it. And I will fill in the missing words. In an isolated system, let me write the words that I want in capital letters. Isolated system, comma, the total linear momentum is conserved. They just wanted you to fill up the words, but otherwise it's pretty much one and the same thing. Nothing too hectic about that. So that becomes your answer. You write it down. In an isolated system, the total linear momentum is literally conserved. Perfect. Okay. That's 4.2. 4.3 says the following. Calculate the speed. Calculate the speed of the combined trolleys immediately after the collision. The combined trolleys immediately after collision. Let's work it out. So it's the linear momentum equation. There we are. Remember they said ignore the effects of air resistance. The system is isolated. Perfect. Now, when the crate gets to point P, it is moving at a velocity of 6.26, which is the one that we found in 4.1. It collides with a stationary 2 kg block, which is this one. So let's get the momentums initially and try to work out finally. Work it out. So I'm looking at 1.5. Oh, direction, please. So let's say original direction is positive. You can even say right. Original direction is positive. So the crate is moving to the right. So original direction is positive. Or you can say right is positive because that's also clear in the diagram. I am going to give you a question to try anyway after this. So get ready. Original direction is positive. All right. Let's go. Mass of the trolley of 1.5 kg. The velocity is the 6.26. Somebody's asking, but where did we get the 6.26? From 4.1. The moment the trolley gets to point P, it was moving at 6.26. 6.26. That was its initial velocity at point P. When it's now moving point P all the way until it gets to point B, it was starting its journey with 6.26. The mass is 2, but it was stationary. After collision, we hear that they stick together. Stick together. Meaning we treat them as one thing. Oh, listen to this one, Chuck Nolisi. Listen to this one. We treat them as one system. They stick together. So now the combined mass is now 1.5 plus 2. Then we just want to find their speed. That's what they said, speed of the combined trolleys. The rest is algebra. I'm looking at the speed as a number of 2,68 meters per second. Is that what you got, family members? Talk to me right here, right now. Yeah. Is that what you got, fam? 2,68 meters per second. And again, they say it's speed. So I'm just going to leave it on the magnitude, not on the direction. Speed. If they said velocity, I would have then said direction as well. So it's 2,68 meters per second. That's 4.3. Let's try 4.4. The more we do, the more we know. The less we do, the less we know. Let's do more to know more. Listen to this. I'm ready. All right, I'm taking this out. Now, 4.4 is quite interesting, but let me start with a disclaimer as to how you think about 4.4 from that perspective. Listen to this. The equations of motion, which is what you use or do under the topic vertical projectile motion. I have a full 2-hour video when I was teaching vertical projectile motion from scratch. I deserve a seat in heaven next to Moses for the thing that I've done for you. 4 hours from scratch. Fine. The principles, or rather the ideals of the topic, vertical projectile motion, those formulas are also applicable in any motion, in any movement. In fact, to be even more clear, any typical motion is governed by the equations of motion. The only difference is that under projectile motion, the acceleration is the acceleration due to gravity, whose value is 9.8 meters per second squared. That's the difference. So in dealing with projectiles, your acceleration is 9.8, but anywhere else, it's not 9.8. So the question 4.4, and I'll use equations of motion, reads something to this effect. I'm ready. Calculate the distance traveled by the combined trolleys in 3 seconds after the collision. So listen to this. We hear that when trolleys stick together, they continue moving at constant velocity. Hear my words and hear me well. When they move at constant velocity, here's the implication. Whenever we deal with constant velocity, Chuck Norris, Mamela Chuck Norris, at constant velocity, whenever we deal with that, it means the acceleration is 0. Oh, Kosia, Babela. At constant velocity, the acceleration is 0. Always remember that. You will see this again in the topic, work, energy, and power. Constant velocity, simple means acceleration is 0. What are we looking for? Distance traveled. By who? Combined trolleys. In how long? 3 seconds. When? After collision. Your choice of the equation will depend on the information given. So the formulas to pick will depend. You can use this one, and I'll show you a shortcut to it. VI is all in your formula sheet, plus delta T, plus half A delta T squared. Now, delta X is just how far it went, which is basically a concept of distance. Now, when the combined trolleys move after collision, they move with the velocity of 2.68. They move for a time of 3 seconds. Why did I put 0 here? Tell me. Why is this side 0? Why? Why is this side 0? All right, let me hear your answers. You type your answers. Yes, acceleration is 0. And why is the acceleration 0? It's constant velocity. Said it in the question. Constant velocity. The rest is algebra. The rest is maths. Delta x, how far they went, distance. I'm looking at 8,04 meters. That's your answer for 4.4. 8,04 meters, man. Yeah. Talk to me now. Talk to me. Just so you may understand this even further, listen to me. Whenever you hear constant velocity, and now you know the acceleration is 0, you can even use the simple formula that we learned in grade 5, I think. Distance is speed times time. So hear me out. Whenever you get to a point where they say the velocity is constant, please note that you can use this formula. Distance is speed times time. You get the same answer, 2.683, and that gives you 8,04. Why I wanted you to note, it's the same concept here, just that lana ngifaka zero, because the acceleration is 0. So why I wanted us to use this one, I wanted you to know, remember that every topic is interrelated. And because the velocity is constant, that means so is the acceleration. So at the end of the day, that's when you will pull through and understand that the acceleration will be 0 because the velocity is constant. This is something that you need to remember, all right? And these basics are very important. So somebody says, say, if we're not told that the velocity is constant, can we use gravitational constant? No. If you use gravitational constant, you are assuming that when these trolleys are moving on the ground, they are a projectile, and that's not true. In fact, when they move in the ground, they are not a projectile at all. When they eventually stop, it's due to the fact that friction, oh my word, this is from the topic work energy and power, due to the fact that friction is working on the object. That's it. So you cannot use 9.8. You can't. You cannot use 9.8 because it's going to assume that it's a projectile. When the object is on the ground, it is not a projectile. Projectiles are objects that are moving up, down within the air, and the only force acting on them is the force due to gravity. All right, thank you so much for those questions, wonderful questions that we have right there. I'm going to give you something to try. I'm going to give you something to try. Go ahead, I'm listening.
So why are we using the final velocity when the formula says initial velocity?
They say it after collision. After collision. After collision is when the objects move together and their velocity is 2.68. So if you consider after collision, then their velocity is their initial at 2.68. Is that okay? So it's after the collision. That's why you're using 2.68. So you're looking for the velocity after collision. Here's a question I want you to attempt. It's quite a number of marks. I'll give you 7 minutes. Good luck. 7 minutes. There's a diagram. Do your thing. 7 minutes. I got your back. Start now. You are doing this on your own. I'll come back to do it and help you. But you're doing this 7 minutes. 3 more minutes. All right, most people are saying they're done, so let's just go straight to it and see how far we can go. So you got the whole scenario and all the calculations that are given. Nothing too hectic. It's not too difficult. It's a doable question. Calculate the momentum of the car before the collision. Calculate the momentum of the car before the collision. Now, if we look at the diagram or the graph itself, you will notice that there is the 20 meters per second, meaning that it's a straight line graph for a good 5.5 seconds. The car was moving at a constant speed or velocity of 20 meters per second. Basically, that's it. 20 meters per second, and it's moving to the left, by the way. Okay? All right. So now, and for this question, I'll just say left as positive. So the direction where the car is moving, let me just call it as positive. Doesn't really matter. You can call right as positive. It will be the same idea, different signs, but the same values. So I'll say left as positive for the sake of just throwing the spanner into the wheels. All right. So 20 meters per second is the constant velocity for a good 5.5 seconds. The graph is straight. And we're looking for the momentum of the car before the collision. Momentum will be the mass of the object multiplied by the velocity. 1,300, I said, to the left is positive, is moving at 20 meters per second. So we're looking at 26,000 kilogram meters per second. That becomes your answer and is to the left. Because I said left is positive. If you say the right is positive, you'd get an answer which is negative, but it's still the same idea from there on. That's 4.1. Remember, it's your discretion. 4.2, you let me know where there's a problem. Calculate the magnitude of the velocity of the pickup truck before the collision. Now, something interesting happens between 5.5 seconds and 5.7 seconds. Something interesting happens there. At 5.5 to 5.7, there is a change in the velocity. Now, it moves all the way from 20 meters per second and changes to a value of -9. Also, it means by extension, not only did the velocity change, but so did the direction. It's a -9, which now it means it's moving to the right, because we said left is positive. So it's a -9. All right. It's up to you to write what you want. And I've been saying it. You can say left is positive. You can say right is positive. You become consistent on that. It's up to you. Perfect. So now, -9, when there is a change in the direction and the velocity of the object. So we're looking for what? The magnitude of the velocity of the pickup truck before the collision. Let's do some physics here. Momentum initial, momentum final. Remember, I'm still taking left as positive, Mina. I'm still taking left as positive, just to show you the dynamics that come with it. Now, the momentum of the car before collision, we know it, is 26,000, the one we found in 4.1. Then now we're looking for the momentum of the truck, 2,500. Its initial velocity, we don't know it. Actually, that's what we're looking for. Then we hear that after collision, the two vehicles move together. So after collision, the two vehicles move together. And they are moving together at a velocity of 9 meters per second, -9 due to the direction. So now I will say to myself, is the 2,500 from the truck plus the 1,300 from the car, and they are moving at -9 meters per second. We're looking for the initial velocity, the velocity before collision of the pickup truck. My math, if correct, gives me -24.08 meters per second, and as magnitude 24.08 meters per second. And I think it will be to the right. I'm over answering here, but they only wanted the magnitude. I keep getting this question, say, is it compulsory to put left as positive? No, Chuck Norris, it's up to you. You get the same answer. It's up to you. It's up to you. It's up to you. All right. Write this one down. So what is interesting to note is that there's changes in velocity. When we're moving from 20 meters per second, now we are at -9. And this particular decline, or the graph going down, indicates that particular change in the velocity. 24.08, check out and see if you're on the right track. Correct yourself where you're right, wrong, and take it up from there. Confirmed, is that 24.08 meters per second? Is that 24.08 meters per second? Is that a yes or a no? Right, I say yes, thank you. All right, perfect. 4.3, calculate the magnitude of the net force on the car. Calculate the magnitude of the net force on the car. All right, your choice of the equation will depend on the information given. Net force. Okay, so the formula says net force times time is change in momentum. You can quickly write it like this if you want. So the change in the momentum over the change in the time. When the collision takes place, please note that the force that the car exerts on the truck is the same that the truck exerts on the car. So whether you use the information about the truck or the information about the car, you will get the same answer. Mass change in velocity over the change in the time. There we go. Mass VF minus VI over time. Now, when the collision took place, there was a force that was exerted, there was a change in the velocity. But how long did the collision take place? How long? So the concept of time. So work with me. We are at 5.7. Then there's 5.5. So the change in the velocity took place here. The difference between 5.7 and 5.5 is a time of 0.2 seconds. So for 0.2 seconds, there was a collision. For 0.2 seconds. 1,300, I'm using the car information. Final velocity is -9 minus the initial, which is a +20, minus from the formula. And your answer is -188,000. Confirm if right or wrong. 500 newtons And as an answer is 188,500 newtons. And it will be to the right because we said left is positive. I just over answered on that one. Please do let me know if we're on the right track from there on. All right, perfect. So you can use the information about the truck. You'll get the same answer. I used the information about the car. I got the same answer as well. So either or is fine. Go ahead, I'm listening.
So I think you made a mistake on 4.2.
What mistake did I
Now,
make?
can you please redo 4.2, sir?
The answer is 24,08. Recheck calculation. That's the correct answer. 24,08. Yeah, recheck your calculation. All right, perfect. Let's keep going. All right, go ahead. I can't hear you. Guys, I prefer you type. Can I just say that? Just type your question. All right. And all. Say, why can't we leave the force as a negative answer? You can. You can. But the answer wanted the magnitude. So write the value as it is. The negative just simply shows you direction. It's not negative as in it's a negative number. It's negative, which is an indication of the direction. So they wanted the actual value, 188,500. All right, perfect. 4.4. Determine by means of a calculation whether the collision is inelastic or it's elastic. Inelastic or it is elastic. Now listen to me very carefully. Now, when a collision is elastic, it simply means in that collision, the kinetic energy is conserved. So whenever a collision is elastic, it means kinetic energy is conserved. So the kinetic energy that you have before collision and the kinetic energy that you have after collision is the same. That's an elastic collision. If it's inelastic, the kinetic energies before and after collisions are not the same. I spoke about it in my part 1. So if it's inelastic, the sum of the kinetic energies initial cannot be the sum of the kinetic energies final. That means it's inelastic. Let's do some maths. Let me find the initial kinetic energy. It's half mv squared for the truck plus half mv squared for the car. Initial. So I need to get the kinetic energies before collision as well as the kinetic energies after collision. All right, let's go initial first. Let's do the math and you'll take it up from there. Am I getting half? Let me write it here because I need more space. All right. It's half. The mass of the truck is 2,500. The velocity, we're looking at the velocity of the truck. I think we got it as negative 24,08 squared, half mv squared. The car is 1,300. Its initial velocity, don't forget this is squared at the top. Take this out. The velocity of the car, initially we're looking at 20 meters per second squared. Now, I'm not so sure about my answers, but do confirm. If I made a mistake, please do correct me. I'm getting 984,808 joules. Confirmed the initial kinetic energies. Kinetic energy is measured in joules. Correct. Thank you. Let's go after the collision. Half mv squared. So after collision, the car and the truck move together. So the combined mass of the truck and the car and their final velocity, which is the -9. I know because it's squared, -9 will become positive. So remember, after collision, they move together. Confirm my answer, 153,900 joules. Yes or no? I'm not so sure about these answers, yes? Is that your answer there? All right, perfect. So in this case, this becomes the kinetic energy initial, and this is the kinetic energy final. Are they the same? No. So here's your conclusion. It's inelastic. Why is that? The sum of the kinetic energies initial and the kinetic energy final are not the same. They are not the same. So therefore, it is an inelastic collision. Now, just as a disclaimer on this one, all right, just as a disclaimer on this one, I'm not so sure if you will ever find a question where it says it's elastic. You can. I actually have one that like that, come to think of it. You can find a question that says it's elastic. But while that is true, that it can be elastic, it is important to notice that inelastic is the most popular. So don't always think that collisions are elastic. Elastic collisions happen mostly when there's a reaction, which is what I teach under the topic rates of reaction. And I have a video on it on YouTube. You have no excuse to fail. None whatsoever. None. All right. Let's try another question, which will be my last one. I want to do something a bit zipper. All right. So zipper. All right. So that it becomes easier to understand where this is coming from. But I want to do this one. Yes. I want to do this question, which is my last one there. Guys, again, I encourage you to get the basics right. It's difficult to try and learn basics from questions. You need to go back to the question itself so that you can understand where it's the base itself, so you can understand where it's coming from. You can't start building a house from the roof. You can't. You can't just wake up in the morning and decide to run a 100-kilometer marathon. You're going to collapse. 5 kilometers, you are chuluga. Go and give yourself time to run through the basics. They will clarify everything. Everything. Basics. Basics are everything when it comes to understanding questions. Basics. Can't build from the roof. From the ground up. That's how we build. 2016 Metro Central Prelim Paper 1, question 4.1 to 4.3. Tanko Poza, Pezwa. It's a very interesting question. I'm going to do this one with you. Let me know where there's a struggle. I cannot wait to start the paid classes. Now, the paid classes, the questions are deeper, stronger, fiery. This was just basics. These are just your hi, how are you questions. But for the paid classes, we are on fire. The more we do, the more we know. I'm reading. Scientists are investigating the possibility of making use of subsurface nuclear explosive in order to deflect asteroids from possible collisions with the Earth. Such a nuclear explosion was buried beneath the surface. Explosive was buried beneath the surface of an asteroid of mass 3.6 by 10 to the 19 kilograms. Before detonation, a stationary astronaut on a nearby spacecraft measured the velocity of the asteroid to be 5 meters per second towards the constellation of Orion. When the explosive was detonated, the asteroid split into 2 fragments, A and B. The explosive projected the two fragments A and B in opposite direction towards the constellations of Orion and Scorpius with the speed, velocity of A, 8 meters per second, and velocity of B, 2 meters per second, respectively. Note, all speeds are measured relative to the spaceship. Now, let me give a context to this question. All right. An asteroid, basically, this question is quite astronomical, as in there's a lot of astronomical terms. Asteroids, astronaut, stars, constellation of Orion, Scorpius, and so forth. Usually, asteroids are large rocks that are moving in the space, and some of them may be headed towards Earth. Actually, you can detonate them. In other words, you can break that big, large rock into pieces so that it doesn't fly towards Earth, but the pieces fly off outside and do not collide with Earth. That's basically the idea, long and short. So you've got this huge stone. This is before. And this guy would have been going towards Earth, this guy. But then you can, through studies, NASA and all those big space companies, about SpaceX, Nabobanban, they're very big on studying these things. They can actually check them years before they come to Earth, which it's moving at this speed. They send a spaceship with a nuclear explosive. It breaks this stone into two pieces, and the pieces fly off and they do not hit Earth. That's basically the idea. So we have that scenario where there is a stone, asteroid, whose mass is this and whose velocity is that. Upon detonation, it breaks into two pieces, mass A and mass B. We don't know what the masses of A are. We don't know what the masses of B are. All we know is their velocities when they've been broken. Now, the mass A, fragment A, moves towards Orion. The mass B is the one towards Scorpius. So it is important to determine, as you start this question, which directions are positive. I would say, because I see the before and the after, I would say choose towards Orion as positive. So towards Orion as positive. But let's start off with our question 4.1. State in words the principle of conservation of momentum. I think we've done that before. And now, basically, what it simply means, the principle says to us, the total linear momentum in an isolated system remains constant. I'm not going to write it. We've done it about 2 or 3 times before. So that's fine, 4.1. But 4.2 is the interesting one, 5 marks. 4.2. Show that the fragment A has a mass of 2.52 by 10 to the 19 kilograms. Fragment A by the mass of 2.52 by 10 to the 19. Now listen to this and listen to this good. Follow my lead. What I know is that there was this whole huge asteroid whose mass is 3.6 by 10 to the 19. It was broken into 2 fragments, mass A and mass B. I would quickly say the mass of A plus the mass of B is actually 3.6 by 10 to the 19. Angithi, we broke down the rock into 2 pieces, mass A and mass B. That is what I know. Now, if we say towards Orion as positive, then here's what we're going to say. The initial momentum, sum of the final, is always the guy that you use anyway, is the same. Let's go initial momentum. Is the mass of that whole rock, the big rock, and it's the mass of the whole asteroid and the velocity of the asteroid initially. I want to start like that. Then it's the mass of fragment A, velocity of A initial, plus the mass of fragment B, sorry, final, and velocity of fragment B final. So this is what we have. In the beginning, we've got the full asteroid unbroken, his mass, his velocity. After there is a detonation, the collision has taken place, there is the breakage into two fragments, mass A, fragment A, mass B, fragment B. The mass of A and B must be equal to the original mass of the asteroid before it was broken into two pieces. Problem, we're looking for the mass of fragment A, and we must show that it's this amount. All right. Do some math. Work with me. Problem number one. I don't know the mass of A. I also don't know the mass of B. But what? I can make the mass of B the subject of the formula. 3.6 by 10 to the 19 minus the mass of A. I can do that. So wherever there's mass of B, I can write it like this. Since I am looking for the mass of A. So then I will say mass of the fragment before collision, 3.6 by 10 to the 19. Velocity initial, we're looking at 5 meters per second. And it's a positive one because it's towards Orion, this 5 meters per second. Mass of fragment A, which I do not know, times a positive 8, because fragment A moves towards Orion, and towards Orion is positive, plus mass of fragment B, which is now 3.6 to the negative 19, minus a mass of A, multiplied by the velocity final, which is a negative 2. All right. All right. Let's do some maths. Let's do some maths. Come on now. Let's do some maths. So now we do some maths now. And I want you to see what's going on again. The mass of A plus the mass of B should give you the original mass. And Mina, because I had two unknowns, I did not know the mass of A. I did not know the mass of B. I did not know it, right? In this case, I will make sure that where I add them, they must equal to the original mass. And I'm saying to you, mass of A is what I'm looking for. Mass of B. You can take this equation and make MB the subject of the formula. You transpose to the other side. To the other side. You transpose. So where there's mass of B, I will now put 3.6 by 10 to the 19 minus the mass of A. Algebra. 8 times 8 MA is 8 MA. We open the brackets here. Negative 2 times this number. I think you get negative 7,2 by 10 to the 19. Negative 2 times this is plus 2 MA. Then on the other side, you've got 3.6 to the 19 times 5. You should get 1,8 by 10 to the 20. It's algebra now. Just algebra. Then you can transpose. You end up with 10 MA, because you say 8 MA times 2 MA. Then you transpose the other guy with 7.2 by 10 to the 19. You should get an answer of 2,52 by 10 to the 20. The question then says, show that the mass of A is this amount. So you divide that by 10. It actually gives you, confirm your answer, yeah, 2.52 by 10 to the 19 kilograms. And that becomes your answer right there. All right. Talk to me. Go ahead, I'm listening.
Sir, there's another way that you can do that.
I know.
You can no
I know. I know. I'm doing this so that in case you can see what's going on. I know. But go ahead. I know. All right. So I do know the other way. So you see why I want to do this whole long way. So I can get you guys to see in cases how you deal with the algebra. Because that's very important to get to understand that. All right. There's many other ways, not just even there's about 3 ways to do that. Not just 1, 3 ways to do that. So it becomes easier to do this. So just to reiterate one more time where this is coming from, please note, the mass of A plus the mass of B is the total mass of the whole thing before it was broken down into pieces. Yebo. And so now we're saying the initial momentum and the final are the same. So the mass of the original asteroid and its initial velocity is equal to when they break up. They break up into 2 fragments, fragment A and fragment B, all with their different velocities and directions. So the mass of A, velocity of A final, mass of B, velocity of B final. Okay. Now, the problem is I don't know mass of A, I don't know mass of B, but I can make the mass of B the subject of the formula. And this moves all the way from there to there. So then mass of A, and you take it to the other side, you make MB the subject. Then you just put it back. Where there's MB, you put this number, and you open the brackets, and then eventually you get only one unknown, mass A, and then you get your answer as 2.52 by 10 to the 19. That's how you get it as Chuck Norris, and you work on it from there on right there. All right, go ahead. I'm listening.
Can you hear me?
Yeah.
Yeah, I wanted to ask, is the other way easier?
It doesn't matter. It's fine. It's okay. It's okay. Either way.
If you don't mind, would you like show it to us? Because I'm having a hard time.
Okay, let me just say this. Okay, thank you for that question. In line with that. All right, let me just say this, guys. And why I always want to just do one method at a time is because there's like 4 or 5 different ways of doing this. Even an easier method more than the one that I'm showing you now. More than the one that you guys were saying to me. Way easier method than this. But I always want you to see the dynamics of how the maths plays around, how you bring the numbers together and take it up from there. Maybe on the group, I'll show you the other method so you guys can see what's going on. But otherwise, this is the long and short of it, of this question. So be very careful about how you handle this. And also avoid shortcuts. I know there's always an easier way, but avoid it because sometimes the easy way is the wrong way. When it looks too easy, no. When you're flowing too much, nothing flows nicer than wrong answers in the exam. Nothing. What you shy like shy way about? What you shy away na lento. Nothing flows faster than wrong answers in the exam. So be very careful of that. All right, perfect. All right, let me go to the last one, 4.3 right here, right now. Right here, right now. All right, 4.3. I'm ready. Hence, determine the impulse experienced by asteroid fragment A. Impulse experienced by asteroid fragment A. Okay, sure. Impulse. So again, your choice of the equation will always depend on the information that has been given. So we don't have force here, so I'm thinking we'll say impulse as my change in momentum. And the one for fragment A, so mass of A, change in velocity final of A minus velocity initial of A, because change in momentum is mass delta V. Mass of A is 2.52 to the 19. Final velocity of A, I'm thinking is the 8 meters. initial velocity is 5. But say, where'd you get this 5 from? Wait, A was originally here before it broke up. It was here at 5 meters per second. It was there before it broke up. So its initial velocity is 5. Right there, right there. Okay? So it means at the end of the day, the impulse becomes equal to 7.56 by 10 to the 19. And you can write it as Newton seconds, but I did say to you, it's kg meters per second. And it's a positive number, so it's towards Orion. Towards Orion. That becomes your answer for the impulse. You could have used also the information about, I think, B. You would have actually gotten the answer right as well from that perspective. My people. The interesting part, the most important part is what's happening in February. The paid classes. This was just your hi, how are you questions. Man, I got deeper questions than this. I think people are typing will say it's deeper. Oh, you have no idea. It goes deeper than deeper. I've got crazier questions that I'll be doing. And I'll tell you what, you need to get the basics right. Okay? Then you can pick up the story from there. And you start practicing your normal hi, how are you questions. Then you start flying off to the big level 5, level 6 questions, which is what I'm going to start with when we do the paid classes. Someone is asking, but say, what you mean, man? What you talking about, man? What paid class are you talking about? I got your back. I got your back. Danko. Now, so this is what we're going to be doing from the 2nd of February, 250 rounds for 5 lessons, 2 hours long. These 5 lessons. Look at how much you learned with me in just 2 hours. Imagine consistently, week in, week out, not having to wait for the free classes at an affordable price of 250 rands for both mathematics and physical sciences, 250 maths, 250 physical science, 500 both. Then you circle, score, and have assurance of your distinction. I can save you. Will there be more free classes? All right. So there's still some spacing on the left for the classes paid. It will get full, I know, but for now there is still some space left. Thank you guys for the kind comments. Let's give him his flowers. Oh, say Kiboza, say Mara, Danko said this helps a lot. I got your back. I will upload this on my YouTube channel. Danko Siabonga. This has been our lesson. I will stop the recording.